name is Ed Blumdahl, and today I'm going to do a short seminar on an idea of Mr. Einstein's special theory of relativity. It's a conceptual model, or you could say it's a Gedanken experiment, a thought experiment, something that Mr. Einstein and many other scientists have used. I'll try to keep this short and simple, and in it I'll use scientific common sense, or Occam's razor, logic, reason, and scientific principles. There's only a minute amount of mathematics involved, so even if you don't have a math background, you'll be able to follow around. If you have done any work with the special theory of relativity, there's nothing new that I'm really adding other than the perspective. And if you don't have it, hopefully my presentation here and what I bring as evidence and ideas, you'll be able to follow so that my conclusion makes sense. This is actually a separate part from an earlier paper that I wrote with the same title, Breaking the Light Barrier, Adding Velocities Beyond the Speed of Light. So this is something, it carries that one forward a little bit, and I'll tell you where you can get the paper, it's published, and some other information. All this work is copyrighted. If you want to use some of this, I'll give you an email address that you can reach me at and give me feedback or what other comments you might have. Okay, I'm going to use my notes here because I just put it together, and they'll help me to keep this going smoothly. The whole of the special theory of relativity goes back to 1905, and it is built on the idea of an inertial reference frame. So what is an inertial reference frame? It's a frame that moves in uniform motion without any forces acting upon it. It can be stationary, it cannot be accelerating, it cannot be changing its path, and uniform motion. Also, one important factor about an inertial frame is that a person within that frame is not able to do any experiment that would help him or her understand if they were in motion or not. Now, that didn't start with Mr. Einstein. That started for a long time. Exactly where, I don't know, but it's certainly maybe Galileo's time or maybe even the Greeks. I'm not a science historian, but you can ask that. So we have this idea of an inertial reference frame. Keep that in mind. And also the special theory of relativity rests upon two postulates. The first postulate is really called the principle of relativity. Mr. Einstein did not develop this. This is also well known. It simply states that the laws of physics are the same in all inertial reference frames. It's pretty simple. What's happening in one inertial frame, if they're set up together, has to happen in the other. If that doesn't hold true, then people might be able to find out if they were in motion or not, and that would breach the principle of relativity. The second postulate, so the first postulate is somewhat generic. The second postulate applies directly to the special theory itself. And the first aspect of it is that the speed of light for all observers in an inertial frames is the same. In other words, the speed of light in a vacuum of space, represented usually by c, the letter c, the speed of light. The other part that's going to play into what I'm talking about here today is this idea that light, the speed of light, is completely independent of the motion of its source, right? So the speed of light, to Mr. Einstein's second postulate here, cannot be added onto the speed of light so that you can get past or higher velocities than the speed of light. So that's a very important idea, and I said we're going to go back and look at that. Well, so we'll get started. Let's look at what we have here, which is a frame. I don't have very good artistic abilities, so I did the best I could. This could be Mr. Einstein. He's in a frame. He has a laser coming out at the speed of c. There's a meter where this splitter splits the signal going back, so the observer can look at it to make sure it's actually this signal or light is actually traveling at the speed of light. And then what happens here, we'll talk about. The other important aspect of it is something called the Lorentz Factor. And this goes back to Heinrich Lorentz, and it's really a scalar, right? The letter gamma represents this in many textbooks and other books on the special theory. And all it says is that you have a velocity and you have the speed of light, which is a constant. And depending on what the velocity is with respect to the speed of light, it just scales the output that you'd get, time or whatever, up or down. And it just simply, as v increases to c, gamma goes to infinity. Mathematicians would probably say that's nonsense, but we'll just use what the physicists use, and that's just it goes to infinity. As velocity goes to 0, gamma goes to 1, and what you end up with is you'd end up with like t is equal to t. That's all. Now, you'll notice something else, that every aspect of Mr. Einstein's special theory of relativity uses the Lorentz factor, or gamma. Time delay, length contraction, relativistic mass, the energy mass, equivalence equation, and even the Lorentz transformation. I didn't write it out, it's simply here. The Lorentz transformation is a function of gamma itself, if you set up the equations. You can find how this, the Lorentz factor is derived. There's a couple of ways you can do it with math. You can do it with geometry. So I'm not going to go into that right now. So, So I'm going to start here in frame A. And what is going on here is, as I said, let's say this is Mr. Einstein. He has a laser. There's a meter to make sure this is what speed this is coming back at. A splitter. So half the signal will come back, the other half will go forward. So what happens? Well, we can take a look at a simple situation where, let's say instead of the frame is going at the speed of light, let's say it's 0, right? It's not moving. If Mr. Einstein turned on the laser, then what you'd get here is simply the speed of light, right? This would go out through the splitter, half of it, at the speed of light. Whiteboard is wet. Also, So never get your whiteboards wet. Anyway, it's going out at c. Now, we could also say, well, what happens if Mr. Einstein doesn't turn on the laser? This platform is going at the speed of c, so the target over here would also know that that's the speed of c. Now, so we know that. I mean, one is c, the other is c, so we know it would go out at c. The question arises, well, what happens when if this is going at the speed of light, and this is going at the speed of light, what happens out here, if anything? You know, is it c? Is it something different? Is it more than that? What is it? We'll come back to this, right? Physics would say, and currently with the special theory, that even though you have c here, you have c here, what would come out of this? You can't add these. It would simply be c. Right? That's where physics would take us today. Using what? Using the Lorentz factor, also the velocity addition equations, which I don't really use here. You can look it up in any basic book, textbook, high school on special relativity, and it will show you how to derive the velocity addition equations. So right now, physics would say this plus this equals this. Why? Because no speed, you can't go faster than the speed of light, right? Back to Mr. Einstein's second postulate, that the speed of light, right, which is here, is independent of the source, basically what's here, right? So it turns out to be c. That's where we'd stand with physics today. Well, so I'll leave that for a little second, or a little while, and we come back down to here, right? Let's say, you know, I forgive the art here, but like I said, I have no artistic ability whatsoever. Let's say we have another frame down. This is A frame. This is B frame, right? Mr. Einstein is here. It's a golf club, supposedly, and he has a ball here, a golf ball here. Instead of taking off at the speed of light, let's say it starts at a very low velocity, you know, 50 miles an hour or whatever you want, but it goes in levels. So in order to keep it at an inertial frame, it has to have uniform motion. So you can start off at 100 miles an hour or whatever it is. You go up to 500 motion. Every time it goes up a level, Mr. Einstein hits the golf ball. Now we know for classical mechanics that if you, in a frame such as this, you add the velocity, right, Newtonian physics, you add the velocity with the speed of the golf ball to attain how that would be perceived by the target over here, right? And, all right, so that's true. Now, but what happens as the velocity increases in this B frame towards c, the speed of light, which is what this is going up here? You know, what happens? Where will this always hold? If we said that the speed of light, right, is independent of the motion of the motion of the source. Here's the source down here, it's the frame. As this approaches c, what you're really asking is, where does classical mechanics end, right, for low velocities, and where does relativity pick up, right, like that? Where is it? Where is that line? Where's that demarcation line where it flips over? And then the question comes up, why? I mean, why at some particular point would that happen? Why at some particular point would that happen? Well, let's leave that off for a second. So this will be going towards the speed of light. We have to answer that question. What happens? Where's that point between classical and relativity? Well, there's two things you should know. One is James Clerk Maxwell published some equations on magnetism, electricity, and light. And Mr. Einstein was very aware of this. In fact, he built a special theory on aspects of Maxwell's equations as we know them. There's a set of 4. And, you know, if we're looking, is this true that the velocity plus the speed of light, or I'm sorry, the speed of the ball equals some v prime? Is it also true that if the platform is going at the speed of light, Mr. Einstein hits the golf ball? From a tee, a golf ball goes off at about 150 miles an hour. So as he approaches C, will the golf ball still go off? Right? So C plus the speed of the golf ball will equal C prime. You add these two together to get C prime. Well, there's 2 things. Maxwell did make a discovery that said the speed of light was the same as electromagnetic radiation, electricity, right? It was the same speed. Call it the speed of light, but it's represented by C. But one thing Maxwell never said was you can't add the speed of light with the motion of its source, which is what physics is today, right? The second postulate of Mr. Einstein, that light is independent of the motion of its source. So keep that in mind, right? Maxwell never said that you can't add them together. The other part about this is, as this is a thought experiment, when Mr. Einstein was 16, from what we understand, he also did a thought experiment. And that thought experiment was that he was traveling alongside a beam of light. And when he looked over, so he's traveling at the speed of light, when he looked over, he said he saw the accompanying electrical field frozen or stationary. So he said, or thought to himself, that can't be right from what I know about Maxwell's equations. And so he came to the conclusion that you can't go faster than the speed of light. It just simply isn't permitted, right? That's the upper bound. Well, that's true to a certain point, but let me make another analogy, right? What happens if there's a train and there's an open flat car on this train, and you have Mr. Einstein, you have a young child on a tricycle, and you have an observer stationary to the movement of the train? Mr. Einstein, if this child sets off, Mr. Einstein could catch up with him, and if he looked at the child, let's say they're going 3 miles an hour, he could walk beside the child on the bicycle, and he would look, if he just took into account the child, he could say the same that what happened on the light beam, right? You look there, there's the child moving, right? You're moving, but the relative speed difference between the two is 0, right? So so that would be, okay, so that would be 0. But what Mr. Einstein failed to grasp as part of this thinking is that the special theory is really built on perspective. Where's the observer? Is there any motion? What frame are they in? 3-dimensional space plus separate time. And what are they viewing? The frame, the system, where is that? It's all about perspective. So although it's true, that on a light beam, you look aside, you'll see the electric field may be frozen. The same with Mr. Einstein going with a bicycle or a tricycle, right? The velocity is 0, it's the same. But the observer on the bank that even Mr. Einstein used as a thought experiment, a train, what would he see? If the train is going 50 miles an hour, right, he wouldn't perceive the movement of Mr. Einstein and the child as 3 miles an hour. He would view it as 50 miles plus the 3 miles an hour, so it would be 53 miles an hour, right? That's classical mechanics, right? There's nothing special about that. So when Mr. Einstein, from my perspective, Mr. Einstein got it half right, but he lost the big picture, right? how do you get the big picture? You add, if someone's separate from the frame, you add the velocity of the motion of the source plus the speed of the source to get what? The total speed. So if we're asking what would happen here, right? And how do we answer that question, right? So Mr. Einstein's argument is incorrect. So you're asking, as this goes to C, what's going to happen? As this goes to C, where's that line, that demarcation between the classical mechanics and relativity? The answer is there isn't one. There is no line of demarcation. What you do in a sense like this, as you go to C, Mr. Einstein will keep hitting golf balls, even so the speed will be the speed of the platform, or motion of the platform, plus the speed of the ball will be greater than the speed of light. The relativity, based on his argument, doesn't even fit in here. So that's the reason why. What will come out here, right, when he hits the golf ball, you just go to the target at whatever speed they are. So, is there a barrier? That's another question. In other words, what is that barrier? That if you go beyond the speed of light, what happens, right? Well, let me bring in another experiment, which was, in science, it was a useful moment. It was, yes, I'll just say useful moment. I digress a little bit just to give you some background on how sound ties into this. The British actually had jets, or working on jets, before World War II. The Germans actually had a workable jet fighter, the Me-262, which is a successful jet fighter. It came too late in the war to do any good, but the technology was there. So at the end of the war, countries, including the US, shifted from piston drive propellers into jets. And as they made them faster and faster, it came up to, well, what are we going to do about will we be able to break the sound barrier? A bullet can break the sound barrier. A .30 caliber bullet goes about 2,800 feet per second, so that's twice the speed of sound. But can we form a craft that will do that? I tried to look up to see how many test pilots died trying to do this. But of course, the concern was building the aircraft strong enough, right? But it was also, well, is there a barrier? Are we going to hit that? If we hit the barrier, are we just going to bounce off of it? Is the plane just going to crash? Do we go into another dimension? I mean, what do we do with that? We don't know. Well, on October in 1947, a World War II pilot by the name of Chuck Yeager got into a craft called the Glamorous Glennis, and he did what? He was the first person to break the sound barrier, right? The barrier was broken. He went beyond the barrier. I think it was a short time, 20 minutes, but he went beyond the barrier. That was the first time. The craft didn't break up. It didn't go into a different dimension. It didn't hit and crash, right? So this idea of a barrier was just gone, right? Now, take an F-16, which is the basic fighter for the US Air Force, and it goes at Mach 2 plus, twice the speed of sound, right? So that's broken. There's a direct correlation, maybe even parallel, to what happened with the sound barrier and what happened with the light barrier. I mean, one thing you should know, I've done this for 15 years, so this is just the way I see the world. It might be new to you, but I've been doing this for some time. So when you, although this doesn't contain light, right? We have a platform, at sea, we have a golf club. You know, it goes beyond that. So at this point, you're going right beyond the speed of light with just the platform and an object. What happens with light? So we'll go back up to here again. Well, you have to understand something. Light is not a wholly physical phenomenon. It is just another physical phenomenon. And it's finite, right? In a sense, from the physical standpoint, it's the speed of light. There's nothing within that. It makes it holy that you can't touch it, you can't work with it, or you can't, whatever else you want to do with it. So, knowing that what we do here, what happened on the train with Mr. Einstein and the child, that you add the velocities, here Mr. Einstein's argument is incorrect. He didn't see the big picture. He saw a piece of it, but not the big picture. So what happens up here? Well, like I said, there is no barrier here. And the question is, I suppose, is there a barrier here, when you use actual light? Well, there's nothing holy about light. It's going to follow the same path as this concept down here about a platform going to sea. So how do you add this, right? There's nothing to do with relativity whatsoever. This is going at c, right? The speed of light. We already stipulated that, right? Laser is turned on. It works. It's going to go out at what? The speed of c. The meter says the laser is doing c. What's going to happen? That's going out. From what we know that I've been talking about, what do? With relativity gone, it's just classical mechanics. You add c plus c, and you get 2c. That's the answer. That is the correct answer. Now, let's say in frame D we have Richard Feynman. Richard Feynman has a laser in his hand. The velocity of the platform is 0. In other words, he's stationary. He turns on his laser, the laser light will go out. Well, what's special about this? Well, this is an inertial frame. This is an inertial frame. That's an inertial frame. They're all inertial frames. So when he turns on the laser here, the laser has to go here too. Why? Because they're both inertial frames. If it works here, it has to work up there. What you can't have is going back to what the idea or the understanding is now. This can't go here and just stop for some reason, right? It's not going to end there, because if this just stopped here, then you'd say, well, sure, the platform's at C, this would be C over here. That can't happen. This reference frame of Richard Feynman transports up to here, and so this has to go through the splitter. It goes out to the target will measure it at 2c. That's correct. Well, if I see it as correct, and you actually can add the velocities of the speed of light with the motion of its source, I put it in the extremes here, just because sometimes it's easier to see it in an extreme situation. But if you made this 0.5c, it'd be the same. Instead of 2, it'd be 1.5. It doesn't matter. The qualitative analysis would be exactly the same anytime v is greater than 0. It's not going to change. The absolute value would change. What the target would perceive will change, but the qualitative analysis won't change at all. So here you have light going out, 2c. Well, what would happen over here? Well, you can see if you take this, stops the speed of light basically at the boundary, the speed of light. By the way, there is no barrier here, okay? Let me break this up. When you talk about barriers and looking at this, the barriers there's a mental barrier, because if you're in physics or have anything to do with physics, What is, the rule you've always learned about special theory of relativity? The speed of light is the upper bound speed of the universe, and nothing can go faster than that. Right. That's a mental barrier. Mathematics. Well, they have the Lorentz factor. They have the velocity addition equations. That's a mathematical barrier based on a faulty assumption, right? Mr. Einstein made a mistake, right? So there's a mathematical barrier, that you might get stuck in. There's a technical barrier because we don't have a craft that can actually go at the speed of light, right? It's far less than that. And as far as physical barrier, there is no physical barrier. Just like the speed of sound, right? Oh, what are we going to do? We passed it. Oh, what is going to do? It can't happen. We can't have it. There is no barrier, right? It's sort of your mind and the technology, right? It'll go ever faster. Where? I don't know. When? I don't know. This is like if you're, the argument before, if you're, let's say there's a person in a truck and it's going 60 miles an hour. If there's a person on the back of that truck throws a baseball at 60 miles an hour, right, and somebody is ahead on the road, that ball will reach him, and what's the speed? The speed will be, you add them together, 120 miles an hour, not 60 miles an hour. That's what science today would say, but that's not true. So you would say 60 miles an hour. In this and in this, you have to incorporate all the information. If you say this is C, something's missing, right? You have to incorporate the speed of the laser and the speed of the platform, right? You just can't write it off with an equation. So what happens up here with the truck and the person throwing the ball, you have to incorporate both of those. Even with C, it's not holy. It does exactly the same. You have to incorporate all the motion, everything within this information to get to that. So where does this go? Well, it goes back to here. But you can see if this is correct, that becomes a big problem, right? I mean, you can do the math and see. Now, what about the STR? Well, we already said the special theory of relativity uses, in every aspect of it, the Lorentz factor, gamma, right? That should be time dilation. Time dilation, length contraction, relativistic mass, energy mass equivalency equation, Lorentz transform uses a function of gamma. So what happens to all that? It goes away. It's gone. We don't need it anymore. And it doesn't hold up. This is not reality. This is reality. It's always been that way. And it goes back to what Maxwell, right? He never said you couldn't add the velocity, the speed of light with the speed of the motion of its source, right? That's what I want you to get at. This is gone. It doesn't hold up anymore. This is true. We broke the sound barrier. We break the light barrier, right? It's the same basic idea. All right. And then, let me just get this. And then you'll say, well, what about all the experiments that have happened? I don't know how many papers have been written about the time dilation, but I'm sure there's in the thousands, if not the tens of thousands. I haven't read them all, but I've read enough. I have two well-known experiments done that you can find online, and you can read through them. I'll point out a few pitfalls here. You read it and come to your own conclusion. The first one is measurement of the relativistic time dilation using mu mesons. Today we'd call that muons. Frisch and Smith. It's in the American Journal of Physics, number 31, 1963. I don't know what volume, 31 volume, 1963. All right. Well, I mean, I'm not going to go into the entire experiment. I'm just going to say this, that when they conducted the experiment, and they say this, as I read through it, I mean, I came to this, and here's what the problem is. They say, you can see how it's set up as a scintillator, and they managed to, they had a very small opening, time opening for these muons to come through. But they said this, for every particle which decays in the scintillator, hundreds of particles pass straight through without stopping. What they're saying here is that for every one that they counted, which were in 100, like 500, there are hundreds that they didn't count because they couldn't count. So what did they do? They just wrote them off like they didn't exist because the experiment couldn't work with them. That is just data bias, or that is just sampling bias. In other words, they basically kept the ones that they could, and all the other data they just threw out like it didn't matter. I mean, that's a sample bias problem. I mean, that's a high school problem. I hope that these were two PhD physicists, and I hope they had the best intentions, but that's a simple error that they made. And because of that, the paper that they did back in 1963 is actually nullified. They couldn't control much, the hundreds, right? They couldn't control that, so they just pretended they didn't exist. That's not science. That's pseudoscience. That's not science. Now, the other one is also known, well known. It's around the world clocks, atomic clocks, predicted relativistic time gains by Heffel and Keating. It's in Science, volume 177, number 4044, July 1972. And it's actually two papers. It consists of a predicted paper, and then they wrote another paper after the experiment and what was observed. Again, I'm not going to go through this. You can find it yourself, look it up and read it. There's two major problems with it. The first problem is that they were doing both the special theory and the general theory in the same system simultaneously. You can't do that. They might have tried to, fudge it a little, but there are two jetliners. One flew east, the other flew west. And they took the total time and whatnot. But, what should I say? They were, excuse me one second. Like I said, this was, okay, there I am. One was the predicted paper and one was the observed papers. But you can't simultaneously analyze a system using both the metric of the special theory and the general theory. Why? Because these were commercial aircraft flied east to west, and the commercial jets are in a curvilinear path under acceleration in a gravity field. That has nothing to do with the special theory of relativity, right? We talked about that, an inertial frame. Uniform motion and no forces acting upon it. Acceleration, gravity, forces, a curvilinear line. For an inertial frame, it has to be a straight line. So that has nothing to do with the special theory of relativity. The other point is that since these were commercial jets, and this experiment was sort of done on a shoestring, these planes took off, but they had passengers on it. So they had to stop, unload the passengers, refuel the plane, get a new crew, and then eventually take off again. Both were the same. And they did this several times. Well, they talk about the total time that it took for each plane to go around the, circumnavigate the Earth, and then they had flying time. Go look it up. Look up the flying time and look up the total time it took, which means that there's a big period of rest. They don't account for that. In other words, the atomic clocks that they had on the experiment, which is about time delay, sorry about that, I should have said it earlier, was about time dilation. They make no way to account for that time when they were down and they weren't traveling. There's other problems with the paper. I would say you can't use that as something to verify the special theory of relativity because it's the way they set up the experiment is too many problems with it, and it says really nothing. Now, I've gone through a lot of different experiments, and I've looked at them, and I've told the scientific community this. You show me an experiment that purportedly demonstrates the veracity of any of special theory's aspects, time dilation or any of these, and I will show you an experiment that went wrong, just like these. I think it happens to be somewhat of a human nature that we tend to find things that we want to see. And the same happens with science. We want to see things or see things so bad that we actually find it. And a lot of other experiments are the same way, right? There's problems with the experiments, and so they don't really back up Mr. Einstein's idea of the special relativity or back up special relativity at all. They all fail. The special theory of relativity is not a direct representation of physical reality. I guess that's what I'm getting at, right? That's gone. All right, closing in the end here, what I want you to get out of this, right? I want you to get out that it is possible to add the speed of light with the motion of its source. I've written other papers on this. You can do it. You can go faster than the speed of light. In fact, you do it all the time. It's just so minute, right? If you're driving a truck and you hold out a flashlight, I mean, to some extent, it's true. You're just not going to really be able to find it. So, so that's number one. You can go beyond. There is no barrier. C is not the upper bound speed barrier. There isn't one. It doesn't exist, just like the sound barrier. Mr. Einstein made an incorrect choice when he looked his reasoning for why nothing can go faster than the speed of light. And that was the problem, and that's been part of the problem with physics and the special theory all along. I do have, if you go on the web to this, www.ieee.org, that's the Institute for Electric and Electronics Engineers. And they have the paper, Breaking the Light Barrier, Adding Velocities Beyond the Speed of Light. It was written in 2005, and it's listed under E.A. Blumdahl. Or you can use this address, right, and go directly to the paper. So you can just copy that down if you want to see it. I think it might cost something for you to get it, but it's there. It's published. If you have any questions or comments, or you want to use some of this, you can send them to eabphysics@gmail.com. Let me just say one other thing, okay? This is not an attack on Mr. Einstein. I know he's become basically an icon and a cult symbol and what, but this is an attack on Mr. Einstein. I have great respect for Mr. Einstein as both a scientist and as a humanist. He won the Nobel Award for something called the photoelectric effect. It still stands. I agree with it. His place in science is secure, right? What he gave to science. So when I'm looking, I mean, just as a forward notion, with the special theory of relativity, I very much disagree with that. I tried to point out the reasons. I hope you understand. The problem is the general theory has problems of its own, right? So this is not out to attack Mr. Einstein. This is science. This is the way it's supposed to work. Somebody writes something, you disagree, you show your evidence and put it down. It's not really working well for me, but people don't like what I'm writing. So anyway, that's it. Anything else? No. Oh, I do want to mention one thing also, sorry. You know, the whole idea behind this is that instead of, you know, working in a very small box within the special theory, paying attention to the Lorentz factor and the velocity addition equations and everything that goes with it, right? That you're hopefully, this will free you up. You're not stuck to just the velocity, I mean, the C. You can go beyond that under specific situations, right? I mean, it makes you free to have a lot more work that you can do, work that you can work with it, and I'd certainly be interested in see what other people come up with. If we can go faster than the speed of light, what does that mean? What does that mean for physics, for astrophysics, for astronomy, for cosmology? If that's true, I've actually written papers on it, so if that's true, that opens up a whole field full of what the possibilities are. What does that mean? Will we ever find a unified field theory? We're not going to find a unified field theory with the special theory of relativity and the general theory of Mr. Einstein because they're incorrect. You know, if you want to find it, you have to circumvent those and then go on your own. I don't have much interest in it, but you might. So you're free. You know, think. You know, flap your wings, fly, see what you can come up with. That's one of the ideas. I want to see people, you know, look this over, come up to your own conclusions, whether you agree with it or not. And if you do, take it and go with it. Where can you end up? What can this mean? So I hope it starts a new chapter in the history of science, right? The day they broke the sound barrier, the day they broke the light barrier. Thank you.